In the course so far, we have seen that when X is an affine variety in AN, then its coordinate ring A of X can be calculated as the quotient of this polynomial ring by its ideal. And this ideal is a radical ideal. And in particular, this A of X is a finitely generated algebra because it's the quotient of such a polynomial ring. And it is reduced. Since this is radical, and reduced means 0 is the only nilpotent element. So as an upshot, X affine variety gave us a finitely generated reduced K algebra. And now we're ready to present the construction in the opposite direction. So if R is such a finitely generated reduced K algebra, we claim that we can produce an affine variety X, which has R as its coordinate ring. So to get X, pick any of a set of finitely many generators of R as a K algebra. This uses this part of the properties. And then we obtain a surjective K algebra homomorphism from this polynomial ring to R, which just plugs in these generators into the variables of this polynomial ring. So basically, this is kind of an equivalent characterization of being finitely generated K algebra. And then, so from this surjective homomorphism, by the isomorphism theorem, its image, which is all of R, is isomorphic to the domain divided by the kernel, which we call J. Then the fact, now use the second fact, that R is reduced, tells us that J is a radical ideal. This kind of uses the opposite direction here. Okay, so we have gotten ourselves a polynomial ring and a radical ideal J. And so we are looking for a variety. Well, let's take X to be the vanishing locus of this radical ideal. And this is indeed an affine variety in AN and its coordinate ring, because this is radical. J is also the ideal of X by the Notsternsatz. So indeed, A of X is isomorphic to this quotient, so to R. So we have gotten ourselves an affine variety with this given coordinate ring. The construction now, of course, depended on choice of generators, B1 up to Bn. What if we had chosen a different set of generators? Would we have gotten a different variety? Well, a priori, the answer is yes, because, for example, we could choose a different number of generators. For example, we could just repeat one of them a couple of times. And then we would have gotten ourselves, by the same construction, a variety X prime inside some AM, possibly different dimension. But what would, of course, still be true is that both A of X and A of X prime are isomorphic to the same ring R by the construction. And so we had this corollary which says, well, if you have or somehow we had the corollary which says the isomorphisms from X to X prime correspond to isomorphisms from A of X prime to A of X. And so since these are isomorphic, we know that abstractly as ring spaces, X and X prime are isomorphic, even if they live a priori in different ambient spaces. And so this is a kind of motivation to slightly redefine what we mean by affine variety, to be a bit more intrinsic, to not depend on which exact affine space we sit in. So from now on, an affine variety for us will be just some ring space that is isomorphic to an affine variety sitting in some ambient space in the old sense. And let me remark already that basically all of the structures that we used on affine varieties still make sense for these kind of more abstract affine varieties. For example, we still have a topology, they're still ring spaces, so they have an underlying topological space. We still know what regular functions are. We still know what A of X is because it's just regular function on all of X. And so you'll see that everything that we actually use will still make sense without having this ambient space. except for, of course, having the coordinate functions. This is the one thing that this space gives us. So if this definition, so here, I mean, this is slightly subtle thing redefining something which we have already defined. If you wanted to be very correct here, you could say that what we have called affine variety so far, maybe this should be called an embedded affine variety because it sits inside some affine space AN. And then the new things, we could call these ring spaces isomorphic to an embedded affine variety. We could call these abstract affine varieties. So this would be a bit cleaner, but then also I would now have to use an additional word every time I want to talk about varieties. And so for simplicity, we just keep using the same word, but now it means just these abstract ring spaces. So it's a subtle point, but it is somewhat important. And I wanted to give an illustration. So the embedded affine varieties, so in both cases, the varieties are kind of these spaceships, and embedded until now meant that our spaceship is in a docking station, the affine space. And this was very convenient. We got all kinds of nice services. So for example, we could define the Zariski topology here as the relative topology of the Zariski topology here. We got the coordinate function, which told us where each point of our ship is. But now we have kind of grown out of this. Now we want to actually fly this ship into space. And this is the new concept of abstract affine varieties. They're just on ring spaces. They're not supported anywhere. And we have enough structures built so that we can live on that spaceship. Okay, that's the cheesy pictures describing the change of definition. And then maybe again, a bit more mathematical. We can also have a categorical interpretation of what we just saw. So in the language of categories, we can summarize it as follows. We can define two categories. One is the category affine varieties, whose objects are, well, affine varieties in the new sense, and the morphisms are just morphisms of ring spaces. The second category is more algebraic. It's finitely generated reduced K-algebras, whose objects are, well, finitely generated reduced K-algebras, and whose morphisms are just K-algebra morphisms. And then kind of the culmination of all these results we have seen is that the claim is that you can go from affine varieties to these reduced K-algebras, sending x to R equals to OX of x, so just the full sections of regular functions. And then the morphism f is sent to the pullback morphism, and this goes in the opposite direction. And the claim is that this is a contravariant functor. This is just a code word for saying that the arrows change direction here. And the juicy bit is that this is an equivalence of categories. And this is saying it's bijective on equivalence classes of objects. For each equivalence or isomorphism class of affine varieties, you have a unique isomorphism class of algebras on this side. And how you would prove this is you do this construction that we had before. If you're given R, then you can find an affine variety with this coordinate ring. This shows basically surjectivity. And similarly, you can see the injectivity. And so this is one part, bijective on equivalence class of objects. And then the second part is that the morphisms from X to Y are exactly isomorphic to the morphisms from OY to OX on this side. And this tells you that basically any question you can ask about affine varieties must in some way be answerable by looking at its coordinate ring. This is kind of the deep philosophy that goes back to Grothendieck. So this means that all results in commutative algebra in principle correspond to some results here about affine varieties. The one thing which we'll kind of fix later is that we see the affine varieties. This looks like a very natural, nice category. On this side, this is a very long name, like finitely generated and reduced K algebras. So what we're going to do later is we're going to look at more general rings here. In particular, in principle, there's something on the geometric side which will correspond to the category of arbitrary rings, with morphisms being ring morphisms. And this will be these affine schemes on this side here, and this is what we're going to see later.